Since it blinks, I hope it will start recording now. So today is lecture number 1. And we start with discussion of symmetries. Okay. The target is quantum world. In quantum world, contrast to classical world, we are dealing with so-called indistinguishable particles. So let's assume this statement that the particles which we are dealing with are indistinguishable, and start to draw some conclusions from the point of view of indistinguishability. So for the moment, let's assume that we don't have any interactions. We just assume to begin with two non-interacting particles, and no special topology, which I will be able to touch upon in the second part of my course, which means that we are dealing with a three-dimensional world of non-interacting particles. Say we have particle 1 and particle 2, and we are saying that we are about to find a wave function or characterize the wave function of these two particles. I will denote it by psi as a function of psi1 and psi2, and psi1 and psi2 is set of three-dimensional coordinates and, if necessary, spin of these two particles. So we are dealing with a stationary quantum mechanics, so this wave function is a subject of the Schrödinger equation E psi. And what you know from the course of quantum mechanics is that probability density, something what people can measure, is given by square modulus psi1 psi2. Okay. Let's take a sort of mental experiment and interchange these two particles. Once again, they are indistinguishable, which means that as a result of this interchange, we get a new wave function psi, psi2, psi1, and the probability density is characterized by psi, psi2, psi1 modulus square, and since particles are indistinguishable, we have that this probability density are the same. Therefore, the only difference which can appear because of interchange of two particles is the extra phase. I will denote as I alpha, psi, psi1, psi2. Because of this extra phase, when we square modulus of the wave function, we get the same result. So this was step number 1, this was step number 2, and let's make step number 3. So we take these two indistinguishable particles and interchange them again. So we have 1 and 2. Again, as a result of this interchange, we have psi as a function of psi1, psi2, which, in accordance with the previous step, can only be different from the wave function which we got in the previous step, psi2, psi1. And at the same time, if we use this equation, this is e to the power 2 I alpha psi, psi1, psi2. So, as a result of two interchanges of these two particles, we actually arrived at a very important equation. If we compare the left-hand side and right-hand side of this equation, we conclude that e to the power 2I alpha is equal to 1. Again, no interaction, no topology is involved in this derivation, and this very simple equation has two sorts of solutions. So solution number A is when alpha is equal to 0, 2 pi, 4 pi, and so on and so forth. If we look at that line, we will get that for this solution, psi, psi2, psi1 is equal to plus psi, psi1, psi2. Let me be sure. I'm just worrying that this is blinking. I hope that it will still be recorded. So what we see here, that the wave function of two indistinguishable non-interacting particles is symmetric with respect to interchange of these two particles. Okay? As I said, we are dealing with symmetries. So the system of many-body system of particles characterized by symmetric wave function is called bosonic system. So it's bosons. However, there is yet another class of solutions, B, namely it happens when alpha is equal to pi, 3 pi, 5 pi, and so on and so forth. In this case, we have another property, namely psi, psi2, psi1 is equal to minus psi, psi1, psi2. So by interchanging two particles, we arrive at appearance of the sign minus, which means that the wave function of, in particular case, two non-interacting particles is fully antisymmetric. So these are fermions. So you see that just from the assumption of indistinguishability of two particles, we arrive at some conclusions which allowed two possible solutions. Again, let's proceed further and draw another important conclusion based on symmetric or antisymmetric shape of the wave function. For example, for system of bosons where the wave function is symmetric, I will continue here, we can clearly see that if two sets of quantum numbers, coordinates, well, momenta, whatever, spins are the same, namely if we consider the wave function, and now I will put index B also here, B will denote bosons and F will denote fermions. So for bosons, we can imagine that if we have a set of coinciding arguments, for example, we consider two bosons sitting in the same coordinate place, but this is perfectly allowed. So such kind of wave function can exist because we don't violate this equation putting two arguments equal. So which means that bosons can be characterized by the same set of quantum number, or saying it by other words, there can be many bosons which possess the same set of quantum numbers. And this is what we are going to discuss in the second block of lectures, and in particular this interesting observation results in very important phenomena in quantum walls of bosonic system, which is Bose-Einstein condensation. Contrast to that, if we put two arguments of the fermionic wave function being equal, we come to the equation that psi f psi psi is equal to minus psi f psi psi, which has obvious solution that the function is equal to itself with a sign minus only when the wave function is 0. So psi f psi psi is equal to 0. Which means that for fermions we cannot have the very same set of quantum numbers. If we want to come to description of fermions, say two indistinguishable fermions, nevertheless, at least one of the quantum numbers should be different in order to have a non-zero wave function. And this very simple and important solution of equation is known as the Pauli principle or Pauli exclusion principle. So fermions should be characterized by two fermions are characterized by two different sets of quantum numbers, namely at least one of the quantum number should be different. Okay, when I'm saying fermions on bosons, let's start with some examples. The examples which you discuss in quantum mechanics were mostly related to elementary particles. In particular, electrons, neutrons, protons, neutrino are fermions, and photons, for example, are bosons. However, the spirit of many-body physics or many-body theory course is to deal with excitations. So we will discuss the ground state properties, what is the ground state of the system, and we will discuss also so-called quasi-particles, contrast to elementary particles, and excitations. So basically everything what we are going to do will be about quasi-particles and excitations. And what kind of quasi-particles or excitations do we have in the quantum theory of many-body physics? We already, on Wednesday, we will be dealing with elementary excitations in fermionic systems, which are electrons and holes. So since it's a fermionic system, the excitations have also Fermi statistics. We come to description of statistics in a few minutes. On contrast, there is a big group of bosonic excitations. For example, discussing magnetism, we will see that magnons are bosons. Phonons, which you already discussed very intensively in the course of solid-state physics, are also bosons, and so on and so forth. So you see that this notion of statistics is very important for everything, and in particular is important for description of the excitations in system. And both examples are equally important for our course. At this point, I would like to mention something which I'm not going to prove. It's going beyond beyond the scope of this course. Nevertheless, I would like to refer to it, and it is a connection between the spin and statistics. In quantum field theory, it's called Pauli theorem, and it says and proves that the system subject to fermionic description or Fermi-Dirac statistics are a system with half-integer spins. So here spin is 1/2 or 3/2 or 5/2 or so on and so forth. This is half-integer spin, like we see it on Wednesday, that electrons and holes in Fermi gas, Fermi liquid similar excitations with spin 1/2, while bosonic system bosons are characterized by integer value of spin. So we have spin equal to 0, spin equal to 1, 2, 3. For example, phonons, which you have already discussed, are excitations with spin 0. Magnons are excitations with spin 1. Photons, actually, which are also excitations associated with the fluctuation of electric field, are characterized by spin 1 because light has certain polarization. And of course, there are excitation appearing from the gauge theories. And maybe when discussing some modern physics, quantum Hall, if time permits, we will discuss this a little bit too. Okay, good. Any questions? Let's proceed with the same logics and build up the wave function of two non-interacting indistinguishable fermions and bosons in the absence of any topological anomalies. I'm always adding this word because the real world is a bit more complex in a sense, and what I'm saying with a reservation. For example, those of you who are familiar with this quantum Hall phenomena will immediately tell me that what you are saying is not always applicable to two-dimensional systems, which would be true. Discussing one-dimensional world is another interesting chapter, but I repeatedly say that all these primitive symmetry arguments are applicable for system of n indistinguishable fermions or bosons, absence of interaction, and absence of any topological anomalies. Okay, two bosons. Suppose we have a single particle wave function, we have a non-interacting system, and we build up the wave function of two indistinguishable non-interacting bosons based on phi as a function of psi, which is a single particle wave function. So how we do it? In a very simple way. We write down the psi bosonic psi1, psi2. We need to construct symmetric combination of the products. So therefore we write this is plus 1 over square root of 2, and here it's phi 1 psi1 phi 2 psi2 plus phi 1 psi2 phi 2 psi1. Clearly, if we interchange psi1 and psi2, we immediately see that this term transfers to this one and this one to this one, so the symmetry property of the wave function is satisfied. If we do the same for system of fermions, two fermions, psi1, psi2, we are saying that this is 1 over square root of 2, and here we need to build antisymmetric combination, which is phi 1 psi1 phi 2 psi2 minus phi 1 psi2 phi 2 psi1, which can be written down as a determinant phi 1 psi1 phi 1 psi2 phi 2 psi1 phi 2 psi2, and this determinant has a name. You probably know the name. This is a Slater determinant, correct. And of course, from the course of linear algebra, we know the property of determinants. If you interchange any two rows or any two columns, the sign will change, and this is reflected in the fact that the wave function of fermions is antisymmetric by the construction. Good. We will come to this point a bit later, but if we have, say, system of two fermions or two bosons, and we can factorize coordinate and spin property, spin coordinate and spin dependence, we need to rely upon the general property of the wave function. So for example, if we write fermionic function as a product of spin part, spinors, and coordinate part, we will see that if spin part is antisymmetric, coordinate part should be symmetric, because then the product is antisymmetric, and so on and so forth. So please translate what I'm saying to the system where spin can also be very important player in the game. So now it's quite straightforward to come from system of two particles, which I used as a very simple example, to system of n non-interacting particles, then the bosonic wave function, which characterized by numbers n1, n2, and coordinates xi1, xi2, xi(n), can be constructed p1, pn, phi p1, xi1, phi pn, xi(n). And here there is a normalizing multiplier, n1 factorial, n2 factorial, divided by n factorial to the power 1/2. And we assume that this is a sum of all possible permutations, symmetrized, and we assume that there is n1 particle in state p1, there is n2 particles in state p2, and there is nth particles pn, and sum over I and I is equal to n. So here we explicitly assume that the number of bosons in a given quantum state can be arbitrary. So 0, 1, 2, 3, 4, 5, and so on. The same time, so this is bosonic many-body wave function characterizing system of n non-interacting indistinguishable bosons. For fermions, clearly we need to construct the determinant xi1, xi(n). This is 1 over square root of n factorial. It's a phi1, xi1, phi1, xi(n), phi2, xi1, phi2, xi(n), and this is phi n, xi1, phi n, xi(n). So this is a Slater determinant for system of n non-interacting fermions. And again, based on the properties of determinant, if we interchange any two rows or any two columns, we will get a sign minus, which means that the total wave function of n non-interacting indistinguishable fermions is fully antisymmetric. Good. Of course, another property is if two rows or two columns of the determinants are the same, are equal, then such determinant is equal to 0, and this is what I spelled out as a Pauli principle. So in the system of fermions, at least one quantum number characterizing two fermions should be different in order to have non-zero wave function. Okay? Any questions? I presume that you know all this very, very well. So in the course, sometimes I will come to elementary examples. One of these, and in these elementary examples, I will refer either to quantum box, so particles in quantum box. So what is quantum box? And I will assume that there is no interaction for particles inside the box, but the boundary conditions will be periodic, which means that instead of the box, I will assume sort of torus. And this is a Born-Kármán periodic boundary condition. This is one of the reference system which I will be dealing with, and another system to deal with will be just quantum well with infinite walls, in particular one-dimensional well where the infinite walls means that the boundary conditions are such that the wave function at the boundary is equal to 0. This is what you know from the quantum mechanics. For example, if we will find the spectrum of energy levels solving the single particle quantum mechanical problem in the world, so we then start putting fermions. As I said, on each level we can put only 2 fermions different by the quantum number. So here the energy characterized by K will be h squared, K squared over 2m. As I said, we have 3 particles, but fermions has extra quantum number, non-trivial quantum number, which is spin. So when we start to put fermions on each level, so spin projection on one particular axis, which we will call z-axis, should be different. So we can have 2 fermions on each level, which are different by the spin projection, and this is a Pauli principle. On the other hand, if we put bosons, so this would be a fermionic system. If we put bosons in such a quantum well, of course, in principle, we can put all bosons on the lowest level of the well, and this will be a phenomenon of Bose-Einstein condensation. In particular, this is also possible, which we are going to discuss next week. So whenever I will be speaking about non-interacting particle, I will either speak on the language of box or on the language of the quantum well, whenever it is appropriate for me. So in this case, if we characterize the number of fermions with a particular quantum number k, is a wave vector, so I will denote it at n, k, and sigma. Sigma is spin projection, then nk sigma can be either 0 or 1. So this is 1, this is 0. And so this is bosonic system. And if we speak about bosons, and I'm talking about the same nk, for simplicity I assume that bosons are characterized by spin 0. So I will not put extra index associated with a spin projection. So then for bosons, nk can be 0, 1, 2, 3, and so on and so forth, arbitrarily. So, repeating, starting with assumption on indistinguishability of quantum particles, we arrived at the conclusion that the wave function can either be symmetric or antisymmetric. If it is symmetric, then the quantum numbers and number of particles characterized by the same quantum number can be arbitrary for bosons and can only take value 0 or 1 for fermions, which is Pauli principle. And based on these important conclusions, we now build the quantum statistics for the non-interacting fermions and bosons. Okay? So, in order to discuss properties of quantum gases, and quantum means that we are dealing with indistinguishable particles, we need to deal with certain thermodynamical potential. So I'm going to speak about thermodynamical potential, characterizing it by the index k, and k is the index of the quasi-momentum. This is just kinetic energy. We don't have potential energy. So this is quasi-momentum, and this is energy. Well, this is momentum. Well, quasi-momentum would it be if I use periodic condition, and then I need to write periodic functions like sine and cosine. For the energy, I will construct bands, and so on and so forth. Here, I'm talking about quantum well with infinite walls, namely the boundary condition assumes that the wave function is 0. So this is thermodynamic potential characterized by this K, and this is minus T, say KB, log of the partition function characterized by the same index K. So for all future examples, I will assume the units, the system of units is chosen that the Boltzmann constant, which converts the temperature into energy units, is equal to 1. I will also assume, whenever I say opposite, that the Planck constant is also equal to 1. So such system of units is chosen. Therefore, I will then skip the unit of Boltzmann constant, and the partition function zk is sum over all possible nk e to the power mu minus epsilon k divided by temperature to the power nk. And of course, the total thermodynamic potential is just sum over k, omega k. So this is minus t, sum over k, logarithm sum over nk, e to the power mu minus ek over temperature to the power nk. I hope you are familiar with this notation. Mu is called chemical potential. And in the last 20 or so minutes, based on the fact that the occupation number for bosons can be arbitrary, and for fermions they take value 0 and 1, I will compute thermodynamic potential, and I will derive a distribution function for non-interacting fermions and bosons. Okay? So let's start with bosons. Bosons. So first, zk. This is, as I said, partition function. This is sum over nk e to the power mu minus ek over temperature to the power nk. Ek is this one. So, since nk can be 0, 1, 2, 3, and so on and so forth, if nk is 0, we have 1, then we have e to the power mu minus ek over temperature, then we have plus e mu minus ek over temperature squared, and so on and so forth. So what do we see here is what? Geometric. Is a geometric progression. So the geometric progression converges if e to the power mu minus ek over temperature is smaller than 1. Right? Which means, assuming that ek is a positively defined quantity, ek can be non-negative, only non-negative. We say that mu minus k should be negative, right? Which means that the chemical potential should be negative, because this quantity is always non-negative. So we already come to conclusion that the chemical potential of the bosonic system should be negative. Well, it approaches 0 at some point, and we discuss what happens there. So if we then sum up this convergent geometric series, what we will get? We get 1 divided by 1 minus e to the power mu minus ek over temperature. Good. Now, the distribution function nk bosons, which characterize the average occupation number, is defined as minus d omega k over d chemical potential. So omega k here is minus t logarithm of this quantity. So since it's minus logarithm 1 over something, I will write plus, and I will write 1 minus e to the power minus mu over epsilon k over temperature. Okay, so this is omega k. Plus appears because I have minus and I have a fraction. Okay, if you feel some trouble with the logics, or you cannot understand how the line 2 comes from the line 1, please feel free to interact with me. Because as I said, today I'm dealing with very primitive, simple, basic things, but don't think I will be doing it all the time. Even Wednesday we start real calculations and real lecture, and sometimes if I'm too quick or too slow, tell me. I can either slow down or make things faster. The only and important issue that you need to understand everything, you need to understand logics, you need to understand calculations and be able to reproduce this calculation yourself. Okay? Good. Okay, let's take a derivative. Maybe I put bar, means that this is average. This is minus. Minus temperature. Derivative over log is 1 minus e to the power mu minus epsilon k over temperature. Derivative of argument gives me minus e to the power mu minus epsilon k over temperature. And there is derivative with respect to mu, which gives me 1 over temperature. So minus and minus give me plus. Temperature and 1 over temperature cancels out. I will multiply numerator and denominator by inverse the exponent, and I get nk bar boson is equal to E1 divided by epsilon k minus mu over temperature minus 1. This is what you know as Bose-Einstein distribution function, BE distribution function, which characterize Bose statistics. So this is average occupation number of particles which occupy a given quantum state, characterized by the quantum number k. Good. Okay, let's now assume that this exponent, namely e to the power mu minus ek over temperature, is much smaller than 1. In this situation, nk Bose average, we can then expand the numerator in Taylor series and keep only the first term, which is this exponent, e to the power mu minus ek over temperature, approximately. So this is a limit where the occupation number is much smaller than 1, and what we see here, this is a multiplier a times e to the power minus epsilon k over temperature, and this is a classical Boltzmann distribution, right? So this is Bose-Einstein distribution function, but if we assume that the average occupation number are much smaller than 1, for example, we have a high temperature, the chemical potential is itself logarithm of is huge and negative. So in this case, we are not in the limit of Bose-Einstein condensation at all. We are in the limit that average occupation number for given state characterized by k is much smaller than 1. And we come to the classical distribution function, which is a Boltzmann statistic. So A is e to the power mu over temperature, and in order to fulfill this condition, mu is negative, and also it provides us normalizing factor. The important conclusion is that in the limit of small occupation numbers, the quantum statistics of Bose-Einstein distribution function is limited to the classical Boltzmann statistic. So we have a proper limit of our quantum statistics, which then approach the classical. Okay, this is important. Now let's do the same for fermions. So for fermions, we compute Zk, which is sum over nk e to the power mu minus epsilon k over temperature to the power nk. However, for fermions, we have only two possibilities, nk equal to 0 and nk is equal to 1. If nk is equal to 0, we have 1, and if nk is equal to 1, we have mu minus ek over temperature, and that's it. We have nothing more than that. Therefore, the thermodynamic potential of omega k is equal to minus t log zk. It's equal to minus t log 1 plus e to the power mu minus ek over temperature. Okay? And the total thermodynamic potential, of course, omega k, omega is sum over k, omega k. This is how we get extensive function, and by differentiating this omega with respect to temperature, something we get equation of state. We have everything. We will do it. Some exercise next time. Some exercise I will suggest you right away. So nk fermion bar. So here, hidden, assume that in addition, of course, we will need to have a summation or a spin projection, but in order to derive the distribution function, I assume that this distribution function will be per spin projection. Of course, there is one extra quantum number for fermions. It's not spin 0. Please always remember this, but let me be a bit sloppy in my notations here. I think you forgive me for that. So this is minus d omega k over d mu. So minus and minus. So nk Fermi bar is equal to plus temperature. Derivative of the log is 1 plus e to the power mu minus ek over t. Derivative of exponent is e to the power mu minus ek over t. And derivative of the exponent with respect to mu gives me 1 over temperature. So nkf bar is equal to 1 divided by e to the power ek minus mu over temperature plus 1. So this is a Fermi-Dirac distribution function. Basically what you see that for bosons we have minus here, and again it will be reflected in the fact that bosons can be accumulated in a given quantum state, Bose-Einstein condensation, and for bosons chemical potential is non-positive, so it's negative and it approaches to 0. For fermions, actually, we don't have anything to say about chemical potential right away, except that this is positive quantity in the quantum limit. However, before I come back to discuss the quantum limit, let me do the same exercise as I did here. Let me assume the same condition that the average occupation number for quantum state k is very small, and then I expand this equation, and I expand the denominator, Taylor expand, with respect to this exponent, and what I get that nkf bar is approximately equal to the same exponent mu minus minus ek over temperature, which is a times e to the power minus ek over temperature. And then again, I conclude that in the case when the average occupation number is much smaller than 1, this is a classical limit. The limiting statistics for the Fermi-Dirac statistics is classical Boltzmann statistics. However, now I'm suggesting you one of the exercises. Exercise number 1. Let me write down here nk Bose, which is 1 over e to the power ek minus mu over temperature minus. So I said there is a plus, there is a minus 1. These two classes of quantum gases approach the classical limit in a bit different way. Namely, here we have a minus, here we have a plus. When you expand, in principle, you may write down the equation of motion. This is what we derive for fermions and bosons on some next lectures. But from the equation of motion, you can subtract so-called statistical pressure, which for fermions will be indication of a Pauli principle. So the correction to the classical equation of motion, which is Mendeleev-Clapeyron equation of motion, will have a different sign. And this different sign is because you have minus and plus here. And these two quantum statistics are different because, as I said, in one case you have Pauli principle, in another case you don't, and all this is deeply related to symmetry properties of the wave function. Try. If you didn't do it on your lectures of advanced quantum mechanics or advanced statistical mechanics, you probably did. Did you discuss statistical pressure?
No.
Do this exercise, it's quite interesting, and see how this statistical pressure appearing when you approach a classical limit from two different quantum regimes, namely Fermi-Onnikov bosons. How does it look like? And in principle, in the experiments of ultra-cold gases, which we are going to discuss already next week, people are able to measure this statistical pressure. They measure the state, and this is something what can be directly accessed by the experiment. So exercise number 1, consider this classical limit in a bit more sophisticated way. I mean, you expand more and you proceed with a computation of the pressure. So basically your thermodynamic potential omega is minus P dot V. So this is your thermodynamic equation, and this is where you get the pressure. And the problem number 2, again, you are grown-up people. I'm not going to force you doing anything. This is your responsibility. I can only suggest you something, and I can only advise you doing something, and it's not related to homework. Homework is compulsory. But I'm not in a position to force and control that you are doing that. So one suggested problem, as I said, is statistical pressure, and the problem number 2 is actually related to something what is called Gentili statistics. So I discussed two different limits. Namely, I discussed the limits where nk can take arbitrary numbers, 0, 1, 2, 3, and so on and so forth. And I took another limit, extreme limit, where nk takes number 0 and 1. Problem. Assume that nk can take value 0, 1, 2, up to some finite m. And then in the same spirit, you can compute partition function, you can compute thermodynamic potential, and you can derive the distribution function. And see what this distribution function looks like if you have this generalized type of statistics. If you Google, it's called Gentili statistics. Try to be more towards research and learn something by yourself. Coming back, a few comments about Fermi distribution function. As I said, in contrast to the Bose distribution function, in classic limits, you know that mu is minus some constant, depending on the dimensionality, is t log t. This is a classical value. So chemical potential for classical gases, whatever you have, fermions and bosons in the limit of, in a classical limit, chemical potential will anyway be negative. However, for bosons we already said that the chemical potential is always non-positive. It's negative or zero. For fermions, it's different. We don't have this condition appearing from the condition of convergence of geometric series. We don't have any geometric series here. But what we do have, I replot the quantum well with infinite walls. We start putting fermions inside the well on the state, and so on and so forth, until we put all m electrons. So we fill energies up to certain energy. If we plot the average Fermi distribution function at zero temperature, you see that all states until, so this is energy, this is mu, this is 1, this is 0. So this is a term. This is a Fermi distribution function. So you see that all state until the chemical potential are filled in, and chemical potential is a huge energy for system, say, of 10 to the power 23 atoms. You can make estimation, and we see that Fermi energy of the order of 1 to 10 electron volt. Electron volt is 10 to the 4 Kelvin. So the temperature in crown of the sun is 6,000 Kelvin. So the Fermi, the chemical potential at zero temperature, which is known as the Fermi energy, for the piece of metal like here, is energetically characterized by much higher energy than the temperature of the crown of the sun. However, so the meaning of chemical potential as any potential, it's of course also a function of temperature, that chemical potential of fermionic system at zero temperature is just the energy which you achieve by putting fermions inside your quantum box or quantum well. And as I said, for typical value for metal at temperature equal to 0 is 1 to 10 eV. It's a huge energy. Besides, what we see from Fermi distribution function here, that all states below this energy are filled in, and all states above this energy are empty. Namely, we already found the ground state of fermionic system, and we start with discussing of this ground state next time, next lecture on Wednesday. You may read something about that in Landau Lifshitz Volume 5 or any of your favorite book. And that's all for today. I'm waiting for your questions. I would like to stop here and not to proceed because it would be quite logically to start with this on Wednesday. And on Wednesday what we do, the logics will be like, we start with ideal, namely non-interacting Fermi gas, discuss equation of states and thermodynamics, specific heat, and immediately proceed to the system of interacting fermions, inventing some phenomenological approach known as a Fermi liquid theory, with the idea to map the system of interacting fermions to the system of non-interacting fermions, to see similarities in the ground state, in the distribution function, and also see how effects of interaction can be encoded into two independent parameters, effective mass and the jump of the Fermi distribution function. And again and again, during the whole course, we will discuss excitations above the ground state. And in order to discuss this excitation, we should properly define these excitations. We discuss the criteria when the excitations are well defined. And as a result of this criteria, we will make a simple computation of the inverse lifetime of quasi-particles and see how inverse lifetime of quasi-particles scales, for example, with temperature. Good. If no questions, we are done for today. You have your another lecture which starts at 11, right?
Yes.
So you have some time to breathe and relax before, because the next lecture is lecture by Professor Nersisan. And where you are now, what you are discussing with Professor Nersisan?
Last time we discussed the lower critical criterion for...
low critical dimension?
Yeah, 2D.
So you already discussed lambda phi to the 4 theory, right? And upper critical dimension?
Yes. We discussed that first and lower critical dimension.
Good. Okay, now it's time to push.